Encyclopedia. This is Anagalactic bringing you a supplemental video to help explain the Boscovich force curve just a little bit better. I'm going to read this excerpt from the Encyclopedia Britannica, and this will introduce an associated diagram which I believe will be very explanatory. The diagram, as I've indicated several times, is extraordinarily deep. All the more remarkable that the man who authored the curve that you're about to see lived 2.5 centuries ago. There are physicists in Croatia, Serbia, Italy, the Netherlands, and the United States, and elsewhere, who are studying the Boscovich force curve right now at very high level. So without further ado, let's make this brief. The interaction energy of two protons is shown as a function of the distance between them. At small separations, the energy is positive and the force is repulsive. At intermediate distances, the nuclear interaction is negative and the force is attractive. At distances larger than shown on the graph, and here I'm going to expand this, and now I will complete the reading of the quote from the Encyclopedia Britannica, whose information this is. At distances larger than shown on the graph, the nuclear force becomes negligible, and the repulsive electric force between the two charges is all that is left. This is not Roger Boscovich's curve. It looks like it. And the reason it looks like the Boscovich force curve is that is exactly what it is. It just so happens that they match. His curve is a general algebraic curve solution. And that's one reason I think that he does not include the mathematics in his work. It looks like a coincidence from the human perspective, because that curve, the distance between protons in relation to the interaction energy. The vertical axis is a force. Here they use the word energy because the two terms can be considered to be interchangeable. There is a peculiar relationship between energy and force, which is a much different term, but it is bound to the concept of energy because it is energy that is responsible for force. This leads to a tremendous ambiguity, at least at the language level, in using the word force. I have more than once cited Dr. Sabine Hossenfelder's recent video where she, not being alone at all, makes an entire video devoted to the topic of stating, as often as she can in the least amount of time, that gravity is not, repeat, underline, bold, italic, is not a force. Well, and she's not alone. The long-standing, decades-old ambiguity, which is not settled to this day in science, a blot and a shame on our record collectively, is that we cannot decide as a body of science whether gravity is a force or not. Some of the older textbooks will just state that gravity is obviously a force, which it is. It's very important to actually know why gravity is a force. Centry, C-E-N-T-R-I, petal, is the opposite of fugal, F-U-G-A-L. What is actually happening in gravity? How do you explain gravity, big fat physicist? Well, no two physicists agree on that, unless they're working for the same organization. Then they are forced to agree. They'll agree then because they'll have meetings on what to agree on. But gravity is almost completely undefined even to this day. Newton definitely did not define it. He avoided defining it. Albert Einstein lent his hand in the case. In order to involve another, what would have to be called a linear dimension, time is construed to be a linear dimension in a 4-line system, correct? Well, is that the correct definition of gravity? Of course not. It's a mathematical representation of gravity, which has enormous significance as long as you have a ton of slaves to do the calculus for you. We do. They're called electronic circuits. So relativity is extraordinarily valuable as long as you have supercomputers. Supercomputers are absolutely required. It's hypercalculus. What Einstein saw was a relationship between two spherical dimensions. All physicists to this very day have zero knowledge about the sphere. They never think in terms of spherical geometry, ever. They always think in terms of numbers. So, what we need to do is solve that problem. That is exactly what I have done. In this case, it's the relationship between protons, correlating the distance between them with the interaction energy. This is from Wikipedia, and the title of this diagram is the nuclear force. So the Boscovich force curve is an exact match on the strong force. I don't want to confuse the issue with the confusion that science has caused itself, because currently, and this is typical, there are actually two definitions of the strong force. Just to complete this, in case you're wondering about my reference to the strong force, because you may think it's the other one. And that is not a situation that I caused, and it's not a situation that you and I should have to face right now. But as a presenter, I am forced to expose the errors in our presentation of physical science. And the current use of the term the strong force is allied with a whole group of terms which are designed to have two alternating definitions. And I could make that list, and you can consult it anagalactic.space, because I intend to expand on this topic, because it's so germane to communication, the heart of science. So what the hell is the strong force? If you look into that seriously to get a comprehensive answer, like it was some kind of essay question, say you had a week or 2 weeks to work on this, but it's like 80% of your grade in a class, and your comprehension, full extent of your knowledge of the term, just to define the term strong force, you're going to have 2 sections, because there are 2 completely different definitions of the strong force. And this has to do with the maddening and infuriating domination of the particle physicists who subscribe to the standard model of particle physics, which says that everything is a particle. So, that definition of the strong force has nothing to do even with reality. There's only one correct definition of the strong force, and it was the original definition of the strong force, having nothing to do with pions, gluons, or quarks. Those are mathematical concepts. So, the depiction here of the strong force is the depiction of the proton-proton collision range. Okay? It's a scale model that's scaled to the limit of 2 infinities, 2 intersecting infinities of infinitude are depicted on this graph. And this is the only way to see those 2 infinities, is on that graph. But that is not just a graph of the strong force, defined very precisely as the force relationship between 2 protons. The force relationship between 2 protons. How many such relationships are there if you include the electron as another particle, which it is in this context? There would be 3, wouldn't there? There would be 4 if the electron could be at the center. but the electron is never at the center. And that's why there are only 3 possible interactions. Electron-electron, proton-proton, and electron-proton. The electron-proton should be invertible, because only one can be at the center. But only one actually can be at the center. If you're clever, you'll realize that that 3 represents an orthogonality somewhere. Because electron-electron and proton-proton are both repulsive. Here are 2 protons, they will go away from each other. Here are 2 electrons, they will go away from each other. Correct? Only partially correct, because this is the induction of superposition. You're seeing it in action, the unfolding of the axiomatic basis of quantum mechanics. This is the beginning of superposition, and it works like this. The 2 electrons, if they're put in proximity, this would be at a femtometer range, will be measurably repellent. They will fly away from each other until there is sufficient distance from each other, but they will always continue to move away from each other within the range of the force warp. 2 electrons in proximity have a force warp relationship that forces them away from each other, but that gradually changes over distance. And that's a major discovery by Rudyard Joseph Boscovich that begins to unlock the quantum paradox for modern physics. So that's one of the 2 relationships, minus, minus, put in electrodynamic terms. The electrostatic charge, this is a spooky Gaussian at a distance. They each have a force field, which are now warped against each other. They push apart. 2 protons do the same thing. They push apart. That's the plus-plus and the minus-minus relationship. That's electron-electron and proton-proton. Those are actually extraordinarily different, because, of course, electrons behave differently than protons. The way we can distinguish between this repulsion and this repulsion is that if you push the electrons together to try to make them merge, or make them kiss, or make them pressurize each other, or make them go through each other, but you push the electrons toward each other to try to make them contact, they won't, they can't. That's called the Fermi exclusion principle, although there's a broad footnote to that. But in general, what you're seeing, they will not do anything else except push apart. And they will not get any closer together than the Planck limit. They never touch. Electrons never touch. That means that they're quanta. That means that they're particles. That means that they have numeric reality. They have either position or momentum. But they're there. They're in space. We can tell that they're there. And these 2 things as individual particles repel. Okay, that is also true of the protons until you push them too close together. You cannot push electrons too close together, and that's what the universe says, and that's final. And physicists do not argue that. They've tested it, but the universe is firm about the electron-electron relationship. Those are definitely particles because they cannot be pushed together. Okay? The proton is the other particle. The protons normally repel in basically the same way, although there's a big footnote there. It's actually written in hidden ink, but you and I will be able to read that hidden ink in a moment. But the proton-proton relationship changes. When they're pushed together, they continue to repel. And right up to a certain threshold, a radial limit, really between them, when they're at a certain distance, they will repel. But if that distance is decreased past a threshold, they bind. They just suddenly change their minds and bind. And up to 100 of them will do this together, and neutrons get in on this too. And that is called atomic physics. It produces the periodic table, and it produces molecular physics. Okay, so that's the proton-proton relationship. At the transition zone, where they change their minds and lock, that's what this shows. That's what this curve shows. Where does it show the lock? This is actually a lock. It's many things, and I'll try to teach you all the names of the things that this is. This is the Boscovich inner force curve for two general particles, translated to two protons. But the Boscovich force curve covers another relationship, and it's the one that you and I are far more interested in as astronomers. Now you can see that all of this dovetails together. That's the legacy and beauty of science. It's not a good idea to resist your urge. Spill over your own bounds if you think you need more information. Take up the challenge. Take up the cudgels. Conquer your fear and go into what you're interested in. You won't be able to achieve what you want unless you have that courage. I've certainly had to muster that courage, and if I can do it, anyone can do it. That's just a general recommendation from me to you. I hope you already know that, but if not, this may benefit someone to hear someone sincerely emphasize, don't be afraid to learn. Don't be afraid to extend yourself if you think you need that knowledge. Go for it. Do the work. You'll find the way. All right. So the Boscovich force curve is currently known to have two distinct interpretations. It is now known to be the correct force curve for the strong force, the binding force of two protons. It explains the binding force of two protons. We will explain why this graph shows that. That is why it's produced in Wikipedia, is to show the binding energy between two protons past a certain threshold where the repulsive force turns to attractive force. In the case of the electron-proton relationship, we need to isolate the inner shell, and so we concentrate on the hydrogen atom. 99.9% of the universe, it's estimated, is hydrogen, so it's a good place to start. One proton, one electron. That's also what this curve describes. So it perfectly describes the proton-proton relationship in the nucleus for the binding force. And it also perfectly describes the inner orbit of one electron when it locks into spheric orbit around a protonic force field. And that's what this shows. Either one of those. And all you need to do is interpret the relationship. But it always looks like this. So it's critical, I would say, to understand what this represents, since it represents the two most important physical relationships in subatomic and atomic physics. the relationship between proton and proton in the nucleus that binds them into the nucleus, and the electron-proton relationship, which defines the Bohr atom structure. Those spherical shells are built out, as you know, into what are called the orbital shells, which have suborbitals. And those of you who are blessed enough to be able to study the periodic table into its depth to see what those shells actually mean, that's a world of wonder in itself. The arrangement of electrons around a protonic core all the way up to uranium, where boy, oh boy, oh boy, do we get a big bang out of learning about uranium and plutonium. OMG. There's nothing that human apes like more than to blow things up, especially other people. So that's what we're studying here. Only by accident. I don't think that you're trying to build a bomb. But the people who study this force curve, that's all they think about. So this is a very important curve, both to the good side and to the side that perhaps is the opposite of good. I leave that to you to decide in your sleepy time, or just to, take some Ovaltine, some nice warm Ovaltine, and wrap your shawl around you. I've done this and just muse about what this information is actually being used for to destroy the earth. Well, you and I did not invent that. So as much as we may lament, and I certainly confess to having a lot of emotional distress about these subjects, but that's part of the great balance of life. And in order to have the good, you have to accept the bad. There is such a thing as good luck, but only to the proportion that there is equally such a thing as bad luck. But I'll give you a secret of the universe that I've learned, that good luck always wins out, and therefore there is no such thing as random chance. There is no such thing as random chance. You can roll all the dice you want, deal your cards, bet on your horses or your football games, or compute your stocks, or predict the future, turns of currency, turns of monetary relationships. There's no such thing as probability in the universe. The universe knows nothing of probability. There's no such thing as probability. There's only the certainty that things work. And if you never learn that, it means that you never made it to grade 1 of science. I don't care what your name is or what your title is. Unless you get the big picture, you may end up being less than worthless. You may end up devaluating yourself into the negative category if you're teaching other people the lies that you've taught yourself because you're blind and stupid and you're also proud and arrogant. And so I cite the words of the Dalai Lama. My religion is kindness. So always be kind to those who are so stupid that they don't even know what they're doing to other people with their pretense in science to be know-it-alls. We hate know-it-alls, don't we? What if the know-it-all actually does know-it-all, though? Stay tuned, we have a lot more for you. I'm going to have another presentation about this exact force curve in context, proton-proton, but for the time being, we're going to stay on course and study the electron-proton relationship, because it's the perfect illustration of the brand new geometry and number system that I just discovered in 2022. It's actually shown on this diagram. My discovery. of the spherical number system proves its worth in its ability to interpret this diagram, which I'm just going to tell you in closing, is by far the most important graph ever discovered in physics. And the way I'll be teaching this, it explains everything that is currently not understood. And it's so far-reaching, it reaches beyond the stars and galaxies. It reaches all the way to the end of the universe to explain all the macro-scale objects that are baffling us and dazzling us with their beauty, including the much maligned and much persecuted, most glorious object of all, the leaping panther, currently locked in a cage in a zoo, just pacing back and forth and rubbing its poor, proud hide against the bars and rocks as it's fed dirty, rotten meat and made a laughingstock to children and adults alike. A lion locked in a cage whose name is Supermassive Black Hole. How would you like to have that name if you were a lion? Supermassive Black Hole? What kind of monsters have our scientists become? What's going to become of the human race with scientists so stupid that they've forgotten their vows to whoever they make vows to? Maybe it's just themselves or their dolly. But they're not following the Dalai Lama. They're following their little orange dolly that they, I could name names, but it's all of them. You have to have respect if you want to be a scientist. You don't have respect for a power that's higher than yourself that's guiding you, then guess what? I can see exactly what's guiding you, because something is. And if it's not what we as scientists all hope it is for each other, the highest good, keeping you bound to morality and within bounds of your stupidity and pride, the strong force, huh? The strong force. We're still in the Dark Ages, but Anagalactic is here to bring at least as many as want to go, get out of Dark Ages, and capitalize on the gifts that have been granted to us as scientists of astronomy. We are now capable of understanding the light of heaven, where we get all of our information. And all of the information in your scriptures, which is true, whether it be the Bible, the Vedas, or I don't care where you get your core, your hidden wisdom from, whatever book, it's all made of light. It's all light. And this force curve describes the geometry of light. That's what I want. And so I've gotten mine, mate, but I'm a scientist. And as long as I'm in the ring, you better follow the right lead. Because I'm here now. And I'm going to be published. Thank you for tuning in. Thank you for putting up with me. But this is a very hard decision for me to commit to this kind of level. And so I'm not going to back down to anybody anymore. You either come along, or I'm going to go right over the top of you with my tanks. So tanks for nothing. And we'll be right back. That's enough. Keep looking up. We'll have more on the Boscovich force curve until you understand more than the physicists. Stay tuned.